Okay, hello, welcome ladies and gentlemen. Welcome to our first webinar of summer series. Webinars dedicated to concrete structures. Today we will focus on a beam with an opening. Let me introduce myself. My name is Vlastimil Konečný. I will be your only host today, and I am a product engineer at IDEA StatiCa. We are running on a GoToWebinar platform, so you are muted by default all the time. But in case of any questions, please don't hesitate to ask us. You can write your question to the question panel on the right side of the application. So just very briefly to agenda, we will go through some theory, what is behind the IDEA StatiCa Detail application. I will present you the model of the structure of the beam we will be designing and co-checking today. I will show you how to properly model the structure in IDEA StatiCa Detail application. Then we will go through some thorough results, and at the end of the webinar we will sum it up. So we will do some kind of summary. So let's have a look at the theory, and right now I will turn my webcam off. Right, so IDEA StatiCa Detail application is an application developed with focus on discontinuity regions. As you may know, each structure divides to B and D regions. The B regions are called Bernoulli or beam regions, and here the Bernoulli-Navier hypothesis of a plane strain distribution is valid. So for these regions, you can use classical simplifying calculation to do the design and co-check of such regions. On the other hand, there are D regions. These regions are called disturb or discontinuity regions. And for these regions, the Bernoulli-Navier hypothesis is not valid, and you need to use some more complex method than just simplified calculations. And which part of the structure belong to these D regions? There are, for example.
Plus, I'm sorry that I'm interrupting you, but somebody is telling that you are not sharing, but I can see everything. Can you confirm that you're sharing? I can see that, but
yes, I am sharing my screen. I can turn it off and on again.
Yeah, perfect. We can.
Yeah,
I can see that. I can see that. Yeah. Okay, thanks.
Okay. So as I mentioned, which parts of the structure belongs to these the regions. There are, for example, areas with corbels, areas with sudden change of geometry of the cross sections, frame joints, areas with point load, areas near support, or areas with an opening. And to design and co-check such structure, such regions, these discontinuity regions, the mostly common used method is strut and tie method, where you do the equivalent truss model and do the calculation mostly manually. This is how it may look, and the strut and die method is, as I mentioned, mostly common use method, but it may not be as accurate. It may not lead to satisfactory results, and the main disadvantage is that it can be really time consuming. So that's why we developed IDEA StatiCa Detail application to do such a design in a short time. So what are the main assumptions of the detail application? We assume a 2D plane stress state. It means that each element is modeled as a 2D wall. So the internal forces out of plane are neglected there. We assume that cracks are rotating. It means that each crack rotates over the structure and its direction is perpendicular to direction of principal stress. We assume concrete compression softening. So it means that the concrete is fully cracked before loading by default. Also, we assume reinforcement tension stiffening. And in this case, we distinguish between stabilized and non-stabilized crack patterns. And in both cases, as I mentioned right now, the concrete is considered fully cracked before loading by default. You can see the diagrams in the image on the right side of this screen. We also neglect the concrete tensile strength, and we use stabilized and non-stabilized crack pattern. What are the differences? When there is a stabilized crack pattern, there is a usage of a tension chord model, and it means if the ratio of the reinforcement, the value of reinforcement ratio is higher than critical value of reinforcement ratio, which is approximately 0.6%, then we use stabilized crack pattern, and the reinforcement is able to carry the cracking load without yielding. On the other hand, the non-stabilized crack pattern, it's exactly vice versa. So it means that that the reinforcement ratio value is lower than critical value of reinforcement ratio, and the reinforcement is not able to carry the cracking load without yielding. So these are the main assumptions for IDEA StatiCa Detail application and its usage. And right now we can take a look at the practical example I've prepared for you for today. So I will be designing and code-checking this simple beam. You can see it in a section on this slide. So the total length of the beam is approximately 13 meters, and the supports on the left side, the beam is supported by a column, and on the right side by a wall. When I have created the model in reality, I assumed hinges on both sides of the beam to be on a safe side, but in reality it will be stiffer. So I will show you how to model the structure properly to simulate the realistic behavior of the structure. And on the left side, near support, near the column, there is an opening with parameters 700 and 400 millimeters. The cross-section of the beam is rectangular with a height of 1500 millimeters, and the width of the beam is 250 millimeters. So how to solve the part with the openings? Normally, you will probably use the strut and tie method, as I mentioned. So in this case, we must create an equivalent truss model. But for larger openings, such as this one, it's no longer possible to use one universal equivalent truss model as in case of smaller openings. So the several factors enter into the design, such as the geometry of the opening and a beam itself, the reinforcement of the discontinuity region, the loads, and so on. So it's not really that simple to create equivalent truss model for such larger opening, and I know that it will take a really long time to reach some satisfying results. So That's why I've prepared this example for you to show you how to do design and code check for such structure in a really short time. And how is it possible to model the cutoff of the structures? So in case of focusing on this specific part of the structure with an opening, the best approach is to do a cutoff of this part of the structure and model the beam with trimmed end or trimmed ends. It depends on where you want to do the cutoff, where the opening is placed. And how does it work? You can see some main assumption for a beam with a trimmed end. So the first important thing you need to do is that you must model also the section representing the connection to the related B region. So it's this one. Including loads, loads and internal forces. And this is really necessary to reach equilibrium over the structure to model the beam with all the loads and internal forces as well. So in our case, we are modeling the part of the structure with support. We just need to know the loads and reaction in the support, and the software automatically calculates the value of the internal forces at the trimmed end of the beam. And if you check it with your global model in some third-party FEA software, you ought to get same or really similar values of internal forces as in IDEA StatiCa Detail application. To ensure realistic stress distribution to the analyzed part of the structure, the Sandvenan zone, transfer zone, is automatically created by the software, so you don't need to model it by yourself. And the width of the zone is calculated as a half of the cross-section's depth. And the only purpose of the transfer zone is to have a proper stress distribution to the analyzed section, to the analyzed part of the structure. So there are no result in the Sandvenan transfer zone when you finish the calculation, the analysis. And the edge of the trimmed end is modeled as rigid, so it may rotate, but it must rest plane. And that was all for the theory. And now let's have a look how to model the structure in IDEA StatiCa Detail application. So I will leave the presentation and I will open the Detail application. Okay, I will click on a new project, and you either can select one of the predefined templates or general shape of the structure, but in this case we will use one of the predefined templates. So I will select beams, and I will select the first part, the part of the beam with end support. There are two approaches how to model such structure. The first one is the one I will show you. The other one, you can model the whole structure, including the column, including the wall. So you can model the whole structure, but for these purposes, because we want to focus really on the opening and the area near the opening, so that's why we choose. That's why we go this way. That's why we chose this approach. So I have predefined beam, and I just modify the parameters of the beam. So I will select these two green arrows. I will select the rectangular shape of a beam and set the height as 1500 millimeters and the width as 250 millimeters. The concrete grade stays as C3037. You can always change the concrete grade during the design, or you can edit the parameters of a chosen grade. So you can either edit the parameters with this blue pen button, or you can select other material from the library with the help of these two green arrows. So that's okay. I set the correct length of the beam, so it will be 5.6 meters. And I think that's it. So right now I will delete the predefined support, and I will add an opening with this blue plus button. I will select opening. The shape stays rectangular, and the width is 0.7 meters. The height is 0.4 meters. And right now I just need to modify the position of the opening. So the master region stays M1, since it is the only one there. So I will change the master point to 1. The insert point is 1 as well. And I will modify the position of the opening. So the position in X direction is 2.625 meters, and the Z position is 0.19 meters. And as you can see, it respects the global coordinate system. So the values set for the correct position for the opening respect the direction of axis X and Z. And now I just need to set the correct support, and I want to simulate the column. So I will run blue plus button, and I will select line support. Right now I need to modify it to simulate the column. As I mentioned before, you have two options: either to cut off the part of the structure, so to simulate the column, the support, you need to set the support as a line support, and to reach the most realistic behavior of the structure, we will modify the stiffness of the support. Or you can model the structure with column and a wall on the other side and you ought to have similar results if you calculate the correct stiffness. So what I need to do, I will modify the position on edge. So I will change the whole length to just part of the edge, and the length of the support is 0.725. So it respects the parameters of a column. So the width of the column is 0.725. That's why I set the length of the line support as 0.725. All right. Next thing, I will unselect the compression only spring support, since I don't want to have it there. And I will modify the stiffness of the support with this blue pen button. If I select it, I can override the value of a bending stiffness and a stiffness in a vertical direction. These values are, for these purposes, they are just estimated, and it's up to every engineer to calculate the correct values of stiffnesses which respect the actual structure in a global. So I will set the stiffnesses for 150 in both directions, and that's it from the point of view of the geometry. And we can move on to the loads section. So as you can see, there are two load cases set by default, one for permanent and the other for variable load, and three combinations, one for ULS check and the other two for SLS check for quasi-permanent combination and characteristic combination. So we will leave it as it is, and we will just override the correct values of line loads as well as internal forces. So I will go to load impulses, I check if the current load case is the load case where I want to do the changes. It is, so I will overwrite the value of a line load to a negative 32.4 kilonewtons per meter, and I will modify the position to 0.363 meters to have it on the axis of the column. And I will do the same for variable load. So I will select the other load case, and I will set the value as negative 11.7 kilonewtons per meter, as well as the position as 0.363 meters. So that's it. And right now I just need to set the correct values of reactions in the support. So it means I will set the correct value of a shear force. So for the first permanent load case, the value of a reaction in the support is 261 kilonewtons, and for the variable load case, it's 73.4 kilonewtons. And as I mentioned, if you have such a model in third-party FEA software and you check the values there ought to be same or really similar to these values, which the software automatically calculates to the trimmed end. So that's it. I don't want to change anything in these combinations, but be aware that you need to set the correct combination rule or combination prescription, so you can always add new load cases, and if you want to include them in the combination, you need to edit the combination and set the correct combination rule. Same goes for SLS combinations, but I will leave it as it is. So the factor for permanent load is 1.35, and for permanent it's 1.5. For quasi-permanent combination, there is a 0.3 factor for variable load case, and for characteristics there are ones. So we set the geometry, we set the loads and combinations, and we can move on to the reinforcement. Before we modify the reinforcement set by default, we have two other options. We can run these two analyses at first. So the first one is linear analysis. It doesn't take into account the reinforcement, and it shows you the direction of stresses over the structures. So the red parts, it represents the compression, and the blue parts represent the tension over the structure. And if I run the topology optimization, the software automatically applies the relative change of energy to effective volume of a structure. So it's kind of the results are similar to Strat-and-Tie method, but it isn't Strat-and-Tie method. It just shows you where are parts of the structure in compression, and where are parts of the structure in a tension. And these analyses, they can help you with an correct input of reinforcement. So it can show you where you need to add more reinforcement, or on the other hand, where you can put less reinforcement bars. So this is how the topology optimization looks like. So these blue lines represents structure in tension, and these red parts, they represent the structure in compression. So I will use this input button in the top ribbon, and when you are modifying the reinforcement, you can have the topology optimization or linear analysis visualization turned on, or you can turn it off. So I will turn it off, and I will modify the reinforcement. So the diameter of stirrups is 14 millimeters. I will set the distance out of the column. So this is how you can modify the distances between the stirrups. You can see that they are out of the column, and yeah. So right now I will modify the reinforcement bars at the top edge of the beam, at the bottom edge, and I will add reinforcement bars to the other edges of the beam. So the bottom part, there will be only one layer. The diameter is 25 millimeters. There will be 3 bars in a layer. I will modify the anchorage type, and on the other side, the reinforcement is continuous, which represents this arrow. So that's it. I will do the same for the top reinforcement. So the diameter is 25 millimeters. There are 3 bars in a layer. We don't need to have it encouraged, and that's it. And right now I will just add the reinforcement at the other edges. So I will use this blue plus button. I will select new group of bars. There will be 7 layers with the distance between bars as 170 millimeters. The diameter is 20 millimeters. There are only 2 bars in a layer, and I will change the concrete cover type to user value, and I will use the user value of a cover to have it to have the reinforcement in a correct position. So that's it. And the last, well, not last, I just need to simulate the reinforcement coming from the column. So I will add a new group of bars. There will be only 6 layers with the distance as 130 millimeters. The diameter stays as 20 millimeters. There will be 2 bars in a layer. I will change the anchorage type, and I will change the direction of the bars. So in edge component data, I will select not top edge, but the left edge of the beam, and I will change the concrete cover type to from the settings. So the cover is 25 millimeters, and with this I simulated the reinforcement coming from the column, and these arrows represent that the reinforcement is continuous and goes to the column. You can always check it in a 3D in the top ribbon if you turn on real 3D visualization. So you can see the reinforcement in a 3D. And the last part, I just set the reinforcement over the opening. So I will select gauges around opening. The diameter will be 20 millimeters. Number of bars will be 2. Distance between the bars is 50 millimeters. And there are only two layers, and anchorage length is 600 millimeters. And I don't want to have the diagonal reinforcement there, so I will turn it off. Okay, so I set the reinforcement, and I can move on to check and run the analysis. So as you can see, the analysis will take only a few seconds. And this is completely nonlinear analysis. So the elements are 2D walls, the reinforcement is real and is connected to the edges of finite elements with a multi-point constraint. Right. So we will soon have the results of the analysis. The analysis contains of preprocessor, the analysis and post-processor. And the mesh is the mesh is set by default, and it's not recommended to modify the parameters of the mesh setting. But if you need to, you can always do it in a settings in the top ribbon. So right now we have results, and we can see that this structure overreached the utilization of stress limitation. But if we go to the stress limitation check, we can evaluate whether it is really on some critical point of the structure, or we can neglect such a low value of overutilization. Otherwise, everything else is under 100%, so it means that it's okay. So concrete is 75.1%. The utilization of reinforcement is 80.4%, and the anchorage is nearly 100. So this is a summary check, and we will go really quickly, since we are running out of time, through the each check. So this is a strength check where you can display the ratio of a stress to the limit value of stress. By default, you can see only the critical value, but if you are using version 22 of IDEA StatiCa Detail application, you can display the value over the structure if you move your mouse cursor there. So you can find out the value all over the structure in a place you want. And this is for concrete, and it's the same thing for reinforcement as well. So you can have either ratio of a strain or stress, or you can display the real value of stresses or strain over the structure. Same goes for anchorage check. So you can see the most utilized part of the structure is on a bar around the opening. You can also display the total value of in the reinforcement bars. This is the stress limitation check. So we can see that it's in the top edge of the beam. So if we assume that there is a slab which is related to this beam, there will be more reinforcement in a slab, so we can neglect such a low value of utilization of a stress limitation check. This is how the crack width check looks like. So we can see the critical parts of the structure, whereas the most crack width. And you can also display the value over the structure with the mouse cursor as well. And the last part of the check is that you will get the deflection check as well. So you will know the value of a deflection in a section related to the trimmed end of the beam. And you can display the values for short-term effects, long-term effects, and immediate effects of a variable load or a total value of a deflection. And once you are satisfied with your results, you can go to the bill of materials, where you can see the shape and other parameters of reinforcement used in the structure, as well as overview table, where you will get the total length of the reinforcement, total weight, and for example the reinforcement weight per volume unit of concrete, which can be handy. And of course you can do the report and add it to your documentation. During the process of designing and code checking, you can do your own images, store it in a library, and then apply it here in the report, so you can create your own images as well, not only the predefined ones. And in the report, there are all of the necessary data there. So you can go through all of the important data, and as I mentioned, add it to your documentation. So if I go back to the presentation, let me sum it up a little bit. So why use CSF method? Why is it, I don't want to say better, but quicker and probably much more easier than use, for example, strat and tie method? So the first and let's say most important reason to use the CSFM method is a time saving. So when you are using the simplified methods, it can take you approximately 4 or more hours to design and code check such a structure. But if you use the CSFM method, you can see, you can saw that it took me really, I don't know, 15 minutes to design and code check such structure. So that's a really important factor why to use CSFM method. And another reason is to save and optimize material. So thanks to this method, you may know where you need to add more reinforcement, or where you can afford to cut back the bars. And the last but not least important option why to use CSFM method is that you will get all of the important code checks, including SLS checks, as for example, correct width checks or deflection check. So that's it, and we overreach a time a little bit, so we will skip Q&As, and if there are any unanswered questions, I will answer them after the webinar. So let's have a look what's coming next. I want to invite you to 2 other webinars of this summer series of webinars. So the next webinar will be on August 2nd, and the topic will be dedicated to the corbels, so how to properly model corbels and design and code check them. And the other webinar will be dedicated to code checking and designing the deep beam. So if you want to educate yourself even more, don't miss it. After the webinar, you will receive a short survey, so please fill in this survey. It helps us to make our webinars even better for you. So you will receive the recording, or sorry, you will not receive the recording, but the recording of this webinar will be in our support center under webinar section, or the video will be uploaded to our YouTube channel. And if you don't have IDEA StatiCa yet, you can get the trial version at ideastatica.com, where you can apply for 14-day trial. You will receive the full license of our product, and you can try new things there. And if you want to educate yourself more, you can go to our support center, where we have a lot of important and useful materials prepared for you. So I think that's all from my side. So thank you for attending this webinar, and I hope we will see each other in one of the next following webinars. So thank you, and have a nice day. Bye bye.